Welcome to the deep dive. Today, we're getting into something really fundamental for building modern software. We're talking concurrency and parallelism.
Yeah, two terms everyone hears, but honestly, they get mixed up all the time.
Exactly. And it's not just, academic. If your app grinds to a halt under load, understanding this difference is key. It tells you where to look. So our mission today is to really unpack this. We want to look at why languages like, say, Rust and Go tackle this so differently from the older guards like C++ or Java. And here's the question we're starting with. Imagine your server's overloaded, a critical job fails. How do you figure out if it's bad task management like a design problem, or if you've just flat out run out of processing power?
That's the perfect way to frame it. It really gets to the heart of design versus, well, execution. There's this great quote, I think it was Rob Pike who really nailed it.
Oh, yeah.
He said, concurrency is about dealing with lots of things at once. It's structural. It's how you design your application to handle multiple tasks.
Okay, dealing with things. Got it.
But parallelism, that's about doing lots of things at once, actually executing tasks simultaneously. And the key thing is you need multiple processors, multiple cores for true parallelism.
Right.
Concurrency, though, you can fake it, sort of. You can achieve it on just a single core by switching between tasks really, really fast, interleaving them. It looks like things are happening at the same time, but they aren't. Not really.
Okay, so that illusion of doing things together versus actually doing them together, why did this become such a huge deal? Let's talk about the why.
Yeah, the history here is important.
We need to go back to that pre-concurrent world, right? The early server models.
Exactly. Think of the simplest model. One single thread, like a waiter at a restaurant who has to take an order, bring it to the kitchen, wait for the food, serve it, clear the table, before even looking at the next customer.
Oh, man, yeah. Painfully slow.
And the killer was something called blocking I/O, input-output. Anytime that single thread needed something slow, like waiting for a response from across the network or reading data from a spinning hard drive.
Which took forever in computer time.
An absolute eternity. We're talking milliseconds, maybe hundreds of milliseconds. For a CPU that can do billions of things per second, that's just dead time. The CPU was basically asleep most of the time.
So you had all this expensive hardware just sitting idle. Huge waste.
Massive underutilization. It wasn't just inefficient, it was economically unsustainable as things scaled up. We had to find a way to use those CPU cycles while waiting for I/O.
So concurrency was born out of necessity, really, to reclaim that wasted time.
Yeah.
But then things got complicated, didn't they?
Oh, yeah. You trade that simple performance problem, the waiting for a whole new class of problems, correctness bugs. Suddenly, tasks are stepping on each other's toes.
This is where that cashier analogy comes in handy.
It is. Concurrency is like one cashier juggling two lines. They switch back and forth, making progress on both, but only serving one person at any exact moment.
Okay.
Parallelism is two cashiers, side by side, each serving their own line, actually doing two things simultaneously.
Right. But the danger zone is when those tasks or those lines need to access the same thing, like the same cache register or database record.
Exactly. Shared resources, shared data, that's where the chaos starts. And you get these two classic concurrency nightmares, race conditions and deadlocks.
Ah, yes, the dreaded race condition.
It's so easy to create them accidentally. Think about incrementing a simple counter. Counter plus A looks like one operation.
Yeah, just add one.
But under the hood, it's usually three machine instructions. First, read the current value from memory into a CPU register. Second, add one to the value in the register. Third, write the new value from the register back to memory.
Okay, 3 steps.
Now imagine two threads trying to do counter plus plus at roughly the same time. Thread A reads the value, say 5. Before it can write back 6, the OS switches to thread B. Thread B also reads the value, still 5.
Oh, because thread A hasn't written back yet.
Exactly. So thread B calculates 6 and writes it back. Then thread A wakes up and writes its 6 back. You had 2 increments, but the counter only went up by 1. An update just vanished silently.
And those are incredibly hard to debug because they might only happen sometimes under specific timing conditions.
Nightmare fuel for developers. And the other one is deadlock.
Yeah, classic standoff.
Yeah, like a traffic gridlock. Thread A has resource X but needs resource Y to continue. Thread B has resource Y but needs resource X.
And neither will give up what it has.
Nope. They're both stuck waiting for each other forever. The system just grinds to a halt.
So this whole mess, race conditions, deadlocks, managing shared stuff manually, it was just too error-prone. Something had to change.
Absolutely. Which brings us to the what? How did the major programming languages respond? They basically developed different philosophies for tackling this concurrency beast.
4 main camps, right? C++, Java, Rust, and Go.
Pretty much. Let's start with the old school, C and C++ mess. Their philosophy is basically explicit control.
Maximum power, maximum responsibility.
You got it. They give you direct access to OS threads, things like std.thread or pthreads. These are relatively heavyweight constructs managed by the operating system.
And the focus is raw speed, low-level access.
Top priority. But the trade-off is huge. You, the developer, are entirely responsible for preventing races and deadlocks. You have to manage mutexes, locks, condition variables manually.
Which is notoriously tricky.
Incredibly so. Modern C++ helps a bit with things like RAII using objects like std.lockguard to automatically release locks when they go out of scope. That reduces some errors, but the fundamental burden of reasoning about shared state, it's still squarely on your shoulders. High performance, but high cognitive load.
Okay, so that's C++ kilo. Then you've got Java. What's its angle?
Java's philosophy is more about managed abstraction. It runs on the JVM, a managed runtime environment.
Right, the virtual machine takes care of a lot.
Yeah. So instead of dealing directly with OS threads all the time, you typically use the executor service framework. It's this rich set of tools for managing pools of threads and scheduling tasks.
So higher level.
Definitely. Java gives you higher level synchronization tools too, like semaphore, blocking queue, concurrent hash map. These abstract away a lot of the low-level locking details for common patterns. The focus shifts more towards developer productivity and leveraging a mature ecosystem. Safety is still crucial, but it relies more on these managed components than raw developer discipline like in C++ on.
Okay, makes sense. Now for the newer players, built almost specifically to fix concurrency issues. Let's talk Rust, the fearless concurrency language.
Right. Rust's philosophy is all about compile time safety. This is radical.
How does it work? It sounds kind of magical.
It feels like it sometimes. The core mechanism is Rust's unique ownership and borrowing system. These are strict rules about who owns data and who can borrow it, either read-only or exclusively write.
And the compiler enforces these rules.
Religiously. And crucially, it uses the system to check concurrency safety at compile time. It uses special markers called send and sync traits to determine if a type can be safely transferred across threads, send, or safely accessed by multiple threads simultaneously, sync.
So if your code violates these rules...
It simply won't compile. The compiler will tell you exactly where the potential data race is.
Wow.
The huge benefit is, if your Rust concurrency code compiles, data races are guaranteed to be impossible. It shifts the debugging nightmare from unpredictable runtime crashes to fixing clear errors reported by the compiler before you even run the program.
That's a massive promise. But the trade-off is the learning curve, right? Ownership is famously tricky to get your head around.
Oh, absolutely. It's probably the steepest learning curve of the four. You pay a significant upfront cost in learning complexity, but the payoff is that fearless feeling you can refactor complex current code with much greater confidence.
Okay, Rust bets on the compiler. What about Golang? Go. It takes a completely different philosophical route, doesn't it?
Totally different. Go's philosophy is about communication. They have this famous mantra.
Do not communicate by sharing memory. Instead, share memory by communicating. I love that.
It's brilliant because it flips the problem on its head. Instead of fighting over shared data with locks, Go encourages you to pass data between tasks explicitly.
How does it do that?
Through two main features, Goroutines and channels. Goroutines are incredibly lightweight, user-space threads. You can easily spin up hundreds of thousands, even millions of them.
Way lighter than OS threads.
Orders of magnitude lighter. And instead of locks, these Goroutines coordinate and send data back and forth using channels, which are essentially typed queues for messages.
So data flows between tasks instead of being accessed by tasks simultaneously.
That's the core idea. It makes reasoning about data flow much simpler in many cases, especially for network services handling lots of concurrent I/O operations, which is what Go was originally designed for at Google.
But there's a trade-off there too, isn't there? You mentioned Go sacrifices a bit of raw CPU speed.
Yeah, that communication via channels isn't free. There's some overhead involved in sending and receiving messages and managing the Goroutines scheduler. For tasks that are purely CPU-bound, doing intense calculations, that overhead can be noticeable compared to C++ or Rust's raw potential.
But for I/O-bound stuff.
For I/O-bound tasks where you're mostly waiting for networks or disks, the ability to manage vast numbers of Goroutines efficiently, waiting without blocking OS threads, often outweighs that small communication overhead. The code tends to be simpler and less prone to locking errors, too.
Okay, that paints a really clear picture of the different approaches. C++ gives you raw power, Java gives you managed abstraction, Rust gives you compile time proof, and Go gives you communication channels.
A nice summary, yeah.
So the big question for anyone listening, which one should you choose? If you're starting something new, how do you pick the right philosophy for your project?
Well, first you need a reality check, and that comes from Amdahl's law.
The party pooper law.
Kind of, yeah. It basically says your maximum speed up from adding more processors is limited by the part of your program that has to run sequentially, the part you can't parallelize.
Right. If 10% of your code is inherently single-threaded.
Then, even with infinite processors, you can only ever get a 10x speedup, max. You hit a ceiling. So throwing more cores isn't always the answer. You have to understand your workload's nature first.
Which brings us to those two main types of workloads, IO-bound versus CPU-bound. Let's break that down.
Okay, workload 1, I/O bound. Think web servers, microservices, database clients. Most of the time, these tasks are just waiting. Waiting for a network packet, waiting for a disk read, waiting for another service.
So the goal here isn't necessarily raw speed, but responsiveness. Right. Keeping the system busy while things are waiting. Maximize concurrency.
Exactly. You want to hide that waiting time. While one task waits, the CPU should be working on another. And this is where the lightweight models really excel.
So Golang, with its Goroutines, seems like a natural fit.
Absolutely. Or Rust using its async await features, often with a runtime like Tokyo, which is specifically designed to handle thousands of concurrent I/O operations very efficiently.
And you mentioned a practical tip here, thread pool sizing.
Yeah, this is super important for I/O-bound work. You actually want a thread pool larger than the number of CPU cores you have, significantly larger sometimes.
Why is that? Seems counterintuitive.
Because most of those threads will be blocked waiting for I/O. You need enough threads in the pool so that even when many are blocked, there's likely always at least one ready to run whenever the CPU becomes free.
Keep the CPU fed.
Precisely. There's a heuristic formula folks use. Number of cores, 1 plus wait time service time. That ratio, wait time divided by service time, tells you how much time a task spends waiting compared to actually using the CPU.
Okay, so if a task waits 9 times longer than it computes, the ratio is a 9. You'd want roughly cores, 1 plus 9. So 10 times the number of cores in your pool.
Exactly. It ensures you have enough threads sleeping to cover the waiting periods, keeping the CPU cores saturated with the threads that are actually ready to do work.
That's a great rule of thumb.
Okay.
Let's flip it. Workload 2, CPU bound.
Right. This is your heavy number crunching, scientific simulations, video encoding, complex data analysis, cryptography. The bottleneck here is pure computation. The CPU is pegged at 100%.
So here, the goal is just maximum parallelism. Get as much work done simultaneously as possible, minimize the total time.
Yep. Raw throughput. And this is where the languages designed for performance shine. C++ or highly optimized Rust are often the top choices for squeezing every last cycle out of the hardware.
What about Java?
Java can be very performant too, especially with things like its fork join framework, which is designed specifically for parallelizing CPU-bound tasks effectively across cores.
And the thread pool sizing strategy here, totally different, I assume.
Completely different. For CPU-bound work, you generally want a thread pool size roughly equal to the number of cores, maybe cores plus 1.
Why not more?
Because if you have more threads ready to run than you have cores, the operating system has to spend time switching between them, context switching. And since these threads aren't waiting for I/O, they're all just ready to compute, that switching time is pure overhead. It doesn't buy you anything. It just slows things down.
So match the threads to the cores to minimize waste.
Pretty much. Keep the cores busy with computation, not busy switching between tasks that are already ready to compute.
This really highlights how there's no single best answer, is there? It completely depends on what kind of problem you're trying to solve.
Absolutely. Concurrency, remember, is the design structuring your work to handle multiple things. That design creates the opportunity for parallelism. Parallelism is what happens when you actually have the hardware, the multiple cores to execute those concurrent tasks truly simultaneously.
They work together. Design enables execution.
Perfectly put.
So at the end of the day, choosing the right language or model comes down to aligning its core philosophy with your main bottleneck. Was it raw speed? Is it I/O throughput? Is it developer productivity? Or is it guaranteed safety above all else?
That's the decision matrix.
Okay, so to wrap up, we've seen concurrency is about structure, Parallelism is about execution. We've seen how blocking I/O forced us into concurrency, bringing challenges like race conditions and deadlocks. And we've explored how C++, Java, Rust, and Go offer distinct philosophical answers to manage that complexity. But I want to leave you, the listener, with one final thought to chew on. We talk about Rust's steep learning curve, right? That upfront investment in understanding ownership and the compiler's rules. If that upfront complexity prevents whole categories of bugs, those really nasty, hard-to-find concurrent race conditions that can take weeks to debug later, are you really on a slower development path learning Rust? Or could that initial struggle actually lead to a significantly faster and definitely more reliable outcome in the long run?
That's a really good question. The cost of prevention versus the cost of cure.
Exactly. What's the true cost of development speed versus runtime reliability? Something to think about.